For the last 50 years or so, the absolute greatest minds in physics have been, just banging their heads against a wall trying to solve this problem that, honestly, it really just shouldn't exist.
Yeah, it's a massive contradiction. It fundamentally breaks our understanding of reality, honestly.
Right. Because, like, when researchers measure the universe with a telescope like tracking the orbital paths of planets or watching galaxies drift or, plotting the curvature of light around a black hole, the math works
It's
flawlessly.
incredibly elegant. General relativity is it's highly predictable at that scale.
It's perfectly predictable, but the second they point that exact same mathematical framework at a microscope, aiming it down into the empty, seemingly silent vacuum of space,
The equations literally blow up.
yeah, they produce absolute nonsense. They spit out infinities. I mean, it is the ultimate cognitive dissonance in modern science.
It really is. I mean, we're basically living in a universe that appears to operate under two completely, entirely incompatible rule books.
Right.
On the macroscopic scale, like you said, the universe is smooth, it's continuous, and deterministic. But when you examine the microscopic realm, specifically the quantum vacuum, that smoothness it vanishes entirely.
It's just gone.
Completely gone. You're suddenly looking at this granular, jumpy, incredibly chaotic environment characterized by high-frequency oscillations and these discrete energy states.
So that's exactly what we're doing, a deep dive into our source material today to tackle this exact schism, the century-old war between the smooth, fluid world of general relativity and the jagged, highly energetic world of the quantum vacuum.
And, if you follow physics at all, you know that trying to force these two theories to play nicely together usually results in, well, career-ending frustration.
Yeah, no kidding. I mean, string theory tried it, right? And that demanded, what, 10 or 11 dimensions just to make the math work out?
Exactly. And loop quantum gravity tried it too. But all these previous attempts require what physicists basically call fudge factors.
Fudge factors, I love that term.
Right. They're just arbitrary numbers plugged into the equations for no reason other than to just stop them from producing infinities.
Which, I mean, has to be deeply unsatisfying from a scientific perspective, right?
Oh, incredibly. If you have to invent, invisible dimensions or arbitrarily tuned parameters just to keep your equations from basically self-destructing, your theory likely isn't reflecting the actual structural reality of the universe.
It's basically a mathematical Band-Aid.
That's a great way to put it, yeah.
Yeah.
Band-Aid.
But our stack of sources today centers on this breathtaking, newly proposed unified framework called quantum vacuum relativity. And according to the really rigorous mathematical proofs presented in this research, this framework claims to have actually done it.
Yeah, it claims to successfully integrate general relativity with the quantum vacuum, entirely from first principles. And the kicker is, without a single arbitrary fudge factor.
Which is wild. I mean, the implications of this, they really can't be overstated.
No, they can't. If this framework holds up, I mean, it represents the absolute holy grail of theoretical physics.
Okay, so our goal today is to map out exactly how this theory achieves this synthesis. We're going to establish the classical fluid baseline of Einstein's universe first, right?
Right, and then we'll contrast that with the granular quantum world. From there, we'll introduce the single, highly specific mathematical operator that actually serves as the bridge between these two realities.
Yeah, and then we'll explore the two incredibly different mathematical methods the researchers use to actually prove this framework works. Like, one looks at the universe from a microscopic, fine-grained level, kind of like inspecting individual pixels on a TV screen.
Exactly. And the other approaches it from a macroscopic, coarse-grained level, looking at how those pixels, blur together to create the continuous image we actually experience every single day.
And then finally, we're going to dive into how this newly unified framework solves some of the most frustrating, just headache-inducing anomalies in modern physics, like the proton radius puzzle and that huge crisis in cosmology known as the Hubble tension.
It is a massive intellectual journey, I won't lie.
Right.
But the underlying logic is remarkably elegant once you see all the pieces fit together.
So let's start at the foundation, right? The classical baseline, general relativity. The bedrock of our macroscopic universe.
The perfect place to start.
When most people think of general relativity, they picture that classic high school science class analogy, a heavy bowling ball sitting in the middle of a stretched rubber trampoline, causing a little marble to roll down the curved fabric toward it.
Right, a trampoline.
But I've always found that analogy a bit, misleading, because it literally relies on gravity, like the heavy bowling ball being pulled down to explain gravity.
That is a very, very common trap. The trampoline analogy is fundamentally flawed because it assumes a downward pull from outside the system.
Right, exactly.
A much more accurate way to visualize general relativity is to imagine a massive, room-sized block of incredibly dense, perfectly clear gelatin.
Okay, giant block of Jello. Got it.
Yeah. Now imagine a three-dimensional grid of straight, perfectly parallel lines drawn in ink throughout this entire block of gel. If you force a heavy, solid object like a cannonball into the center of that gelatin, the gel has to stretch and distort to accommodate it, right?
Yeah, the gel would bulge out around it.
Exactly. Those straight ink lines warp and curve around the mass of the cannonball.
So if I like flick a tiny glass bead into that gel, it's going to try to travel in a perfectly straight line, but because the grid itself is physically warped, the bead's path curves toward the cannonball.
That is exactly it. The gelatin is space-time. The curving of the grid lines is gravity. And the really crucial element here is the nature of that gelatin.
What do you mean?
In Einstein's equations, that substance is inherently continuous. It is a completely fluidic, unbroken continuum. There are no gaps, there's no missing chunks, no little stutters in the gel.
Okay, I want to break down the actual math Einstein used to describe that clear gel, because our sources rely heavily on it, and I really don't want anyone listening to get lost in the Greek letters. Let's translate the classic Einstein field equations into something visual.
Good idea.
So, on one side of the equation, we have the geometry of space-time itself, the shape of the stretched gel.
Right. In the literature, this geometry is described using the Ricci curvature tensor, which is denoted as r mu nu, and the Ricci scalar, which is just r.
Okay, r, mu, nu, and r.
Yeah. Think of these terms as the mathematical language used to describe exactly how violently the ink lines in our gelatin are bending at any given specific coordinate.
And the background gel itself, right, like the physical fabric before the cannonball even enters the room, that has its own mathematical representation too.
Yes, that is the background metric tensor, gru mu nu. It basically dictates the foundational rules of distance and time in that space.
Okay, G mu nu. And then there's also lambda, right, the cosmological constant.
Ah, yes, lambda. Einstein originally introduced lambda to keep his theoretical universe static, and then famously called it his biggest blunder.
Right. But we've since brought it back because, well, we realize the universe's expansion is actually accelerating.
Exactly. So in our analogy, lambda would be like an intrinsic underlying tension built into the gelatin itself, constantly trying to push the material apart.
Okay, so we have the geometry, the curvature, the gel, and the tension all on one side of the scale. On the other side of Einstein's equation, we have the cause of all this distortion, the mass and the energy, the cannonball itself.
That is represented by the stress-energy tensor, T mu nu. This term accounts for all the mass, all the energy, the pressure, and all the momentum in a given area.
So T mu nu is the cannonball.
Right. So Einstein's equation is ultimately a statement of perfect balance. The stress-energy tensor, the mass, dictates the Ricci curvature, the bending of the gel, and the curvature of the gel dictates how the mass moves.
But there is a sort of silent partner in all of this, isn't there? A foundational variable that sits underneath every single one of those tensors, the coordinate system itself.
You're referring to X alpha.
Yes, exactly, X alpha. If the tensors are the actors and the props in this play, X alpha is the stage itself.
It is the absolute bedrock of classical physics.
Yeah.
X alpha represents the four-dimensional space-time coordinates. It labels specific events on what mathematicians call a Lorentzian manifold.
Okay, let's pause on Lorentzian manifold because that sounds, pretty intimidating. A manifold is really just a topological space that looks flat up close, even if it's curved globally, right? Like how the Earth looks totally flat when you're standing in a field, but from orbit, it's clearly a sphere.
That is a perfect visualization, yeah. A Lorentzian manifold specifically incorporates time as a dimension that's intricately linked with the three dimensions of space.
And it conforms to the rules of special relativity, right?
Exactly, meaning nothing travels faster than light. But the critical point for our discussion today is that X alpha, this coordinate system on this manifold, is flawlessly continuous.
Smooth gelatin.
Smooth gelatin.
Yeah.
You can pick any 2 points on a number line, no matter how microscopically close together they are, and you'll always be able to find another point between them.
Right.
The stage has no trapdoors, no missing floorboards, no microscopic gaps. It is infinitely divisible and infinitely smooth.
And that smooth stage works brilliantly until we put it under the microscope. This is where the whole quantum problem just obliterates the classical picture.
It really does.
Because if we take our metaphorical microscope and we zoom into the absolute smallest possible fraction of that clear gelatin-like into a completely empty patch of a true vacuum, we don't see smooth, clear gel.
Not at all. We see a profoundly, violently energetic arena. The quantum vacuum is characterized by high-frequency oscillations.
It's boiling, basically.
Yes, it is a bubbling cauldron where virtual particles are constantly popping into existence and annihilating each other just fractions of a second later. It operates on a finite quantum spectrum. It is not smooth. It is discrete. It is very granular.
So we arrive at the million-dollar question, the foundational crisis that has literally stumped theoretical physics for a century.
How on earth do we mathematically embed this discrete, jumping, highly energetic, granular quantum structure into the perfectly continuous, smooth geometry of Einstein's gelatin?
Because if the fundamental bedrock of the universe is constantly boiling and jittering, why don't planets just rattle apart in their orbits? I mean, why does the macroscopic universe feel so smooth to us?
And the failure to answer that specific question is exactly why quantum gravity has stalled for so long. When previous theorists tried to just, jam the quantum vacuum equations into Einstein's field equations, the mathematical clash between the discrete quantum world and the continuous classical world produced runaway infinities.
The math just breaks.
Totally breaks. The energy densities scale to infinity, the probabilities scale to infinity, everything became nonsense.
But the sources we are looking at today introduce a bridge, a totally novel mathematical intervention called the unit harmonic operator, or theta of t.
Right. The UHO is the absolute core innovation of quantum vacuum relativity. It is a single, rigorous mathematical operator that bridges this divide.
I want to make sure we understand what an operator is in this context, because we aren't just talking about like a plus or minus sign here. An operator in advanced math is more like a set of instructions, right? It's a function that eats another function, manipulates it, and spits out a completely new state.
Yes, exactly. Think of an operator as a mathematical machine. You feed a mathematical object into the machine applies a highly specific set of transformative rules to it, and then it produces a modified object.
Okay, so what rules is this machine applying?
Well, the unit harmonic operator, theta of the t, is a set of instructions derived explicitly from the high-frequency vibrational nature of the quantum vacuum.
So how does this machine act as a bridge? Let me try out an analogy here and tell me if I'm on track.
Sure, go for it.
Think about looking at a high-definition digital photograph of a perfectly smooth billiard ball. When you look at that image on your monitor from a normal, everyday viewing distance, the curve of the billiard ball looks flawlessly continuous. The light and shadow gradient is totally smooth.
Right.
So that perception represents general relativity, the smooth gel.
I follow you, yeah.
But if you take your mouse and you start zooming in on the edge of that billiard ball, you zoom in 500%. Then 5,000%, then 50,000%. Eventually, the illusion of smoothness completely breaks down.
The pixels.
Exactly. You reach the underlying structure of the digital image and you realize that the smooth curve is actually built out of thousands of tiny, rigid, square pixels, jagged little blocks of distinct color.
That's a great analogy.
So that pixelated, blocky reality is the quantum vacuum. The true underlying structure is granular, but the macroscopic emergent property is smooth.
And if we apply that back to our framework, the unit harmonic operator, theta of t, basically acts as the mathematical zoom lens.
Exactly. It's the operator that allows the equations of the universe to simultaneously acknowledge that spacetime is made of jagged pixels at the Planck scale while behaving perfectly smoothly at the macroscopic scale.
And mathematically, what the framework does here is just remarkable. It takes this operator, theta of t, and directly multiplies it against the Ricci scalar in the modified Einstein equations.
Okay, wait, so it's directly altering the curvature math.
Yes, it is literally injecting the discrete harmonic structure, the pixelated instructions of the quantum vacuum, straight into the heart of the continuous geometric curvature.
But that seems like a massive risk. I mean, if you inject jagged pixels directly into smooth geometry, shouldn't the math blow up just like it always has in the past?
It absolutely would if theta of t were just an arbitrary guess or a fudge factor. But the framework proves its validity through two distinct, rigorously derived mathematical methods, Method 1 and Method 2.
Okay, so let's dive into Method 1 first, because this is where we look directly at the microscopic, the fine-grained reality.
Right. Method 1 is where we push the zoom lens all the way in. We are looking at the foundational pixels of reality, at the absolute smallest scale, the Planck scale.
And at this incredibly tiny scale, the framework explicitly defines the shape of the unit harmonic operator. It says it is a Fourier series representing a fully rectified square wave of unit amplitude.
Correct.
Okay, let's stop right there. A square wave. When I picture waves in nature, I picture, like, sine waves. A stone dropping in a pond, creating gently rolling, curved ripples. Acoustic sound waves flowing smoothly up and down.
Curves, yeah.
But a square wave isn't a natural curve. A square wave snaps instantly from one state to another, holds flat, and then snaps instantly back down. Are the researchers really arguing that the fundamental nature of space-time has rigid, jagged edges?
They are indeed.
Hmm.
And to understand why reality operates this way at the quantum level, we have to understand what a Fourier series actually is.
Okay, walk it through it.
A Fourier series is basically a mathematical tool that allows you to build any complex shape by adding together an infinite number of simple, smooth sine waves of different frequencies.
Right.
So if you want to build a harsh, jagged square wave, you can actually do it by stacking the exact right combination of smooth, rolling sine waves on top of each other.
It's like building a rigid Lego house out of smooth plastic bricks. If you use enough bricks of the right sizes, the overall shape is a block, even if the components themselves have little curves.
Exactly. But here is the critical, mind-bending detail in quantum vacuum relativity. To build this specific square wave for the UHO, the framework uses a Fourier series that only adds together the odd harmonics.
Wait, only the odd harmonics, meaning frequencies that are multiples of 1, 3, 5, 7, and so on.
Correct. The series sums plus or minus 135, entirely omitting the even harmonics.
Mhm.
The even harmonics mathematically sum to exactly 0, so they literally vanish from the equation. The text refers to this resulting structure as a double-sided Fourier distribution.
I have to push back here a little bit. Why on earth would the universe just decide to throw out half the numbers? Why does nature arbitrarily discard the even harmonics and only build its foundational square wave out of the odd ones? It kind of sounds like the exact kind of arbitrary math trick we were just complaining about earlier.
I know it sounds totally arbitrary until you look at the actual physical mechanism of the quantum vacuum. The vacuum isn't just empty space, right? It is deeply tied to the creation and destruction of matter.
The bubbling cauldron.
Exactly. The odd harmonic distribution is a direct, unavoidable consequence of particle-antiparticle pairs.
Oh, right. Virtual particles popping in and out of existence.
Yes. When the vacuum generates these virtual particles, it never, ever generates just one. It must obey the strict laws of symmetry and conservation. So it always generates a pair, a particle of matter and its exact opposite, a particle of antimatter. An electron and a positron, for example.
But they don't stick around, right?
No, they exist for an infinitesimally brief fraction of a second, and because they are exact opposites, they are magnetically drawn right back to each other. When they collide, they annihilate instantly.
Poof.
Poof. And when they annihilate, the energy that was required to temporarily manifest them is returned straight back to the vacuum. The framework gives a highly specific name to the underlying energy substrate of the vacuum, the dark reservoir of quantum potential energy, or DOQPE.
The dark reservoir, that acronym sounds like a shadowy government agency in a spy thriller.
It's definitely a dramatic name for a very literal concept. Think of it as the ultimate cosmic bank account.
Okay.
The vacuum takes out a microsecond energy loan from the dark reservoir to manifest the matter-antimatter pair. A tiny moment later, the particles annihilate and pay the loan back to the reservoir in full.
Ah, I see.
And because this process always involves highly symmetric but opposite pairs emerging and collapsing simultaneously, the vibrational signature they leave behind in the vacuum inherently aligns with an odd harmonic distribution.
Oh, wow. So the symmetry of the annihilation process physically prevents the manifestation of even harmonics.
Exactly. It's not an arbitrary choice. It's a structural requirement.
Okay, that actually makes perfect sense. The symmetry of the matter-antimatter pairs dictates the shape of the wave. So down in the microscopic dirt at the hadronic scale, the UHO is not a smooth, constant number. It is a wildly jittering, high-frequency square wave.
It is intensely jittering. And because it is a square wave built from a Fourier series, it contains something called Gibbs oscillations.
Gibbs oscillations. Let me try to picture this. If I'm building a harsh square wave out of rolling sine waves, I can never quite get the corner to be a perfectly sharp 90 degrees, right?
Right.
There's always going to be a little bit of overshoot or ringing at the sharp edges where the smooth waves don't perfectly align.
That is an excellent way to conceptualize it, yeah. If you look at the sharp corner of a mathematically generated square wave, the line doesn't just turn sharply. It actually vibrates violently up and down right at the edge before settling flat.
Like a physical speaker.
Yes. Think of a physical acoustic speaker. If you try to force a speaker cone to produce a harsh, digital square wave beat, like an instant snap from silence to maximum volume and back, the physical material of the speaker cone can't move infinitely fast.
Right, momentum carries it.
Exactly. It will overshoot the maximum point, snap back, and physically vibrate or ring for a millisecond at the corner of the sound wave.
So the vacuum itself is ringing from the strain of the square wave.
Yes. At the microscopic scale, the UHO contains this residual ringing amplitude, which is proportional to 1 over n. It encapsulates the complete, discrete spectral information of the quantum vacuum.
But wait, hold on. We are wandering right back into the danger zone here.
Yeah.
If we build this square wave by stacking higher and higher frequency sine waves, what stops the frequencies from just going up to infinity?
A very fair question.
Because if the vacuum can support infinite frequencies, then the energy in the vacuum becomes infinite and our equations just blow up again. This is the classic ultraviolet divergence problem that killed all those previous theories.
And this is where the framework introduces one of its most elegant mathematical guardrails. It's called the quantum vacuum spectral limit, or QVSL.
A hard cutoff.
Precisely. Remember how the residual amplitude of the jitter is proportional to 1 over n? N represents the maximum harmonic mode, the highest possible frequency allowed in the entire system.
Okay.
The framework rigorously proves that the vacuum cannot physically sustain infinite frequencies. There is a structural maximum limit to how fast the vacuum can vibrate before the very nature of spacetime would just break down.
Like how there is a maximum speed limit in the universe, the speed of light. The framework is basically arguing there is also a maximum vibrational limit.
Exactly. The number of modes, n, is strictly bounded by the QVSL. By mathematically establishing this finite limit, the framework naturally regularizes the equations.
So the infinities just disappear.
The ultraviolet divergences, the exact infinities that ruin every other attempt at quantum gravity, simply vanish. They are mathematically forbidden by the structure of the vacuum itself.
That is deeply satisfying. Instead of inventing a completely unobservable 11th dimension to hide all the infinities in, the framework just proves that the universe naturally caps the frequency dial.
And the actual application of Method 1 is incredibly potent, because researchers now have this explicit, fine-grained mathematical structure, a bounded odd harmonic square wave. They can actually derive foundational microscopic realities from pure first principles.
Like what? What can they calculate?
Well, they can use Method 1 to calculate the exact numerical value of the QVSL. They can mathematically derive the exact physical radii of hadronic particles, like the proton and the neutron, without even having to rely on physical experiments.
Wow.
They can even derive the existence of discrete quanta of acceleration, which we will definitely touch on later.
Okay, so method 1 is the ultimate close-up. It validates the pixelated nature of the universe. But, we don't live our lives at the Planck scale.
No, we don't.
We live at the macroscopic scale. We are built of billions of atoms walking on a massive planet, orbiting a giant star. If method 1 proves that the underlying fabric is a jagged, chaotic, buzzing square wave, how do we get back to the smooth, continuous orbits of planets? Why doesn't the Earth's orbit jitter, like a Gibbs oscillation?
And that paradox is exactly why the researchers needed Method 2. Method 2 transitions us entirely out of the microscopic realm and into the macroscopic, coarse-grained reality.
Okay, shifting gears.
Yeah. And to do this, it completely abandons the direct algebraic insertion of Method 1 and uses an entirely different mathematical toolkit known as a variational approach.
Okay, let's unpack a variational approach. How is it different from what we just did?
So in Method 1, we look directly at the explicit, jagged structure of the wave and literally shoved it into the Einstein equations. Method 2 steps back and looks at the behavior of the entire system over time. It relies on a foundational concept in physics called the action principle.
The action principle. Simply put, the action principle states that nature is inherently lazy. A physical system will always evolve along the path that requires the absolute minimum amount of energy.
The path of least resistance. Let me try a different analogy here.
Yeah.
I used to think of the action principle like water flowing down a mountain. It avoids boulders, finds the deepest grooves, and takes the easiest path.
That works for classical physics, sure.
But maybe a better visualization for a vibrating vacuum is, like a massive stadium crowd or a huge structure settling, think of an enormous suspension bridge right after it's built.
Oh, I see where you're going.
The cables are tense, the metal is expanding and contracting, the wind is hitting it. Over time, the entire massive structure shifts, groans, and microscopically adjusts its physical form until the load is perfectly balanced and the stress on every single bolt is absolutely minimized.
That's actually a much better visualization because it implies an active systemic reorganization to find equilibrium. The quantum vacuum is a highly polarizable, highly active medium, but its total energy is finite.
The action principle demands that this boiling vacuum must ultimately settle into its lowest possible energy configuration. In physics, we call this the ground state, or the zero-point field.
Because any deviation from that minimum ground state, any extra chaos or random vibration would demand extra energy, energy the vacuum simply does not have.
Exactly. It has no choice but to self-organize. Because it lacks the limitless energy required to sustain pure, unbridled chaos, the physical vacuum naturally forces itself into a highly ordered, discrete, harmonic spectrum.
It balances itself out.
Yes. This process of energy minimization enforces a strict equilibrium condition, which the mathematical framework denotes as U sub m equals U sub omega.
Okay, what are those variables? U sub m and U sub omega.
U sub m represents the mass energy density of the matter in the space, and U sub omega represents the spectral energy density of the vacuum itself.
Got it.
The action principle forces these two densities to perfectly balance each other, and this act of balancing gives rise to the most important bridging variable in method 2.
Scalar condensate. The scalar condensate. Okay, this is where the math gets incredibly wild. What exactly is a scalar condensate?
Mathematically, it is represented by phi of x alpha. It is a dimensionless scalar field. It is formally defined as the mathematical average of a finite sum of orthonormal harmonic mode functions.
Okay, we just hit a huge wall of jargon there. Let's break that down piece by piece.
Uh,
A scalar field, dimensionless, orthonormal harmonic mode functions.
Let's start with the mode functions. Remember all those allowed, finite, odd harmonic frequencies from method 1,
Right.
the ones bounded by the QVSL?
Yes, the vibrating pixels.
Orthonormal simply means that these distinct frequencies are mathematically independent of each other. They don't destructively interfere or cancel each other out in chaotic, unpredictable ways. They form a clean mathematical basis.
Okay.
The scalar condensate, phi of x alpha, is what you get when you take a spatial average of all those allowed vibrations occurring over a specific volume of space.
And it is dimensionless, meaning it isn't measured in meters or seconds or joules. It is basically just a pure modifying number.
Yes. Think of the scalar condensate as a mathematical film or a modifying medium that basically overlays the entire spacetime stage. And this condensate is what physically bridges the discrete quantum vacuum and the continuous classical geometry of Einstein's gel.
I really want to visualize how a dimensionless scalar average actually modifies spacetime. Let's go back to our block of clear gelatin with the grid lines drawn in it.
Okay, the jello is back.
If the gel is Einstein's background metric, g mu nu, where does the scalar condensate come in? Imagine taking a thick pane of antique, slightly warped, hand-blown glass and placing it right in front of the gel.
I really like where this is going.
If you look through that pane of antique glass, the grid lines inside the gel look slightly distorted. The gel itself hasn't changed. The actual spatial grid hasn't physically moved. But because you are observing it through this highly specific averaging medium, the antique glass, the geometry effectively behaves differently. The scalar condensate is the antique glass.
That is a phenomenal way to explain it. The framework literally multiplies the classical background metric, g mu nu, by the scalar condensate, phi of x alpha.
It bathes the geometry in the glass.
It bathes the continuous geometry in this quantum medium. And when you multiply them, you create something entirely new. The effective metric, denoted as O mu nu.
The effective metric. So, we aren't just taking Einstein's classic equations and blindly adding a quantum term to the end of the sentence like a postscript. We are structurally altering the fundamental syntax of the geometry itself.
Precisely. The geometry has been fundamentally quantum mechanically corrected by the presence of the condensate. And once you have established this new effective metric, you can plug it right back into the standard, heavy machinery of Einstein's differential geometry to recalculate exactly how space curves.
And what does that give us?
When you process the effective metric through the equations, it yields the effective Einstein tensor, or G effective mu nu.
So, G effective mu nu represents the actual final shape of the spacetime curvature once all the quantum jitter of the vacuum has been averaged out and factored in.
Yes. The effective Einstein tensor encodes all the quantum vacuum effects, and it serves as the absolute primary curvature term in the new modified field equations.
But I'm looking for the missing piece here. We've talked extensively about method 2, the action principle, the scalar condensate, and the effective metric. Where is our star player? Where is the unit harmonic operator, theta of t?
Ah, yes.
In method 1, we saw it explicitly as the jittering square wave. Where is it hiding in method 2?
This is the sheer brilliance of the framework. In this
Yeah.
macroscopic method 2 view, theta of t isn't manually inserted as a square wave at all. It emerges organically from the mathematics.
How so?
It manifests as the spatial average of 1 over phi of x alpha over long time intervals.
It's the average of the inverse of the condensate.
Yes. You take the inverse of all that averaged quantum oscillation, and you average it again over a spatial hypersurface, over a period of time that is significantly longer than the tiny rapid vibrations of the vacuum.
Let me stop and really orient the listener here because we have just covered two wildly different mathematical landscapes.
It's a lot to take in.
On one hand, we have method 1,
Mm-hmm.
the microscopic view, where the UHO is a jagged, explicit, high-frequency square wave made of odd harmonics, jittering with the birth and death of virtual particles.
Right.
On the other hand, we have method 2, the macroscopic view, built on the universe's inherent laziness, where a scalar condensate acts like warped glass to modify the geometry, and the UHO emerges naturally as a smooth spatial average.
Exactly.
The most obvious question is, are these two methods competing? Like, did two different teams of theoretical physicists write these, and now they are just fighting over who is right?
Not at all. The central triumph of quantum vacuum relativity is that these two methods are perfectly complementary. They are two completely distinct mathematical pathways that arrive at the exact same physical reality.
So there's no conflict.
There's absolutely no algebraic conflict between them. Never. Method 1 explicitly proves that the discrete, microscopic, pixelated structure of the vacuum exists. Method 2 proves that this underlying discrete structure can, and must, perfectly sustain our continuous macroscopic reality without breaking classical physics.
Wow.
The source text phrases it beautifully, actually. Method 1 writes theta of det explicitly. Method 2 refers to it by description. They are the microscopic and macroscopic reflections of the exact same phenomena.
And the mechanism that allows them to agree, like the mathematical magic trick that saves classical physics from being torn apart by quantum static, relies on something called the law of large numbers.
Yes, the law of large numbers is the absolute savior of continuous reality. Let's go back to n.
N being the harmonic mode limit, the QBSL cutoff that stops the frequencies from hitting infinity.
Exactly. Let's look at the value of n for different objects. If you are calculating the physics of a tiny subatomic particle, like a single proton, the value of n is roughly 10 to the 16th.
10 quadrillion modes. That is a massive number, but it is definitively finite. It is explicit.
Yes, and because it is finite, at the microscopic scale of a proton, the jitter is completely real. The discrete steps matter. The UHO is actively oscillating, and the jagged square wave shape is structurally relevant to how the proton behaves.
Okay, but what if we scale up?
Right, we move away from the Planck scale and observe a macroscopic, non-Planckian system. An apple falling from a tree, a baseball, the Earth orbiting the sun.
At those human and planetary scales, the amount of matter, the volume of space, and therefore the number of harmonic modes involved, it scales up to a number so unfathomably huge, it basically breaks human comprehension.
Precisely. For any observable macroscopic system, n is so astronomically large that mathematically we treat it as n is much, much greater than 1. For all practical purposes in the equations, n approaches infinity.
And what happens to our jagged, buzzing Fourier series when n approaches infinity?
When n approaches infinity in a Fourier series of odd harmonics, all of those wildly rapid, high-frequency oscillations average out to exactly 0.
Just 0.
All of the tiny amplitude deviations, the Gibbs oscillations, the ringing at the corners, the microscopic jittering, they vanish entirely into the average.
The static is completely smoothed over, the antique glass becomes perfectly clear.
Yes.
Yeah.
Mathematically, as n approaches infinity, the unit harmonic operator theta of ETE converges exactly, flawlessly, to 1.
It just becomes the number 1.
It becomes unity.
I have to just marvel at the elegance of that. It is so deeply satisfying. Because the bridging operator mathematically reduces to exactly 1 for all macroscopic systems. Or at least, it becomes indistinguishable from 1 to within the absolute limits of human observational precision. The modified, quantum-corrected Einstein field equations simply reduce back down to the standard Einstein field equations.
Exactly. If you multiply Einstein's tensor equations by 1, you just get Einstein's tensor equations back.
Yeah.
The quantum effects gracefully average themselves out of existence at the macro scale. The integrity of classical physics is entirely 100% maintained.
But I'm going to play devil's advocate here on behalf of our listeners who might be highly skeptical that it's this clean. What about the bedrock, non-negotiable laws of thermodynamics, specifically energy conservation?
Ah, yes.
If you are messing with the background metric, if you are conceding that the foundational fabric of spacetime is vibrating and jittering with virtual particles, don't you risk leaking energy? Doesn't a vibrating system inherently lose energy to friction or heat? Does the universe slowly bleed energy because the vacuum is jittering?
It is the most critical question a skeptic could ask, honestly, and the framework addresses it head-on. Method 2 explicitly yields an exact energy conservation law. Remember how we discussed the action principle?
Lazy universe, finding the lowest possible energy state.
Because the variational approach guarantees that the entire quantum vacuum system has already settled into its absolute minimum energy ground state, where U sub m equals U sub omega, there is no excess energy available to leak.
Oh, because it's already at the bottom.
Yes. Furthermore, because the operator theta of tech converges to 1 at observable scales, the new quantum-corrected effective stress energy tensor perfectly mimics the classical stress energy tensor. The equations prove that the covariant derivative of the effective Einstein tensor is 0,
Which means what, exactly?
which is the exact mathematical proof of energy conservation. The energy-momentum conservation laws are preserved to extraordinary, exact precision. There is no thermodynamic leak.
That's totally sealed.
The universe remains a perfectly closed, balanced thermodynamic system, even with the quantum jitter happening underneath.
That is a staggering intellectual achievement. The math doesn't just work, it aggressively protects the foundational laws of physics while uniting them.
We truly need to step back and highlight why this framework is historically revolutionary. As we mentioned earlier, theoretical physics has spent 50 years chasing unified theories.
Yeah, string theory, loop quantum gravity.
Right. String theory requires you to accept that the universe has 10 dimensions, 6 of which are curled up so tightly we can never ever see them. Loop quantum gravity requires plugging in the Amirzi parameter, a completely arbitrary free number, just to make the black hole entropy calculations actually match.
Fudge factors.
Yes. But quantum vacuum relativity operates with absolutely no arbitrary free parameters. It is the first and only quantum gravity proposal in history with a clear, rigorous mathematical course grading prescription that recovers standard general relativity exactly at the macroscopic scale, without forcing the universe to behave in unobservable ways.
It doesn't cheat.
It doesn't cheat at all. Having two independent, mathematically distinct frameworks, Method 1's algebraic square wave and Method 2's variational action principle, arrive independently at the exact same physical consequences, proves something profound. This isn't just a clever mathematical trick.
It's a structural necessity of the universe. The researchers aren't forcing the math to conform to their ideas. The math is inevitably revealing how the underlying reality is actually built.
Exactly.
Okay, so we've scaled the theoretical mountain here. We've looked at the equations, the square waves, and the scalar condensates. But I want to really ground this for the listener.
Let's do it.
If I'm an experimental physicist working in a lab today, why should I care about this theoretical framework? Does it actually impact measurable science? Do we have real-world applications for this, or is it just beautiful math on a chalkboard?
It absolutely has real-world applications.
Yeah.
In fact, its ability to cleanly resolve some of the most stubborn, inexplicable anomalies in modern physics is its strongest validation. The best example is the proton radius puzzle.
Oh, this is a fantastic piece of scientific drama. Let me set the stage on this one for the listeners.
Please do.
For decades, physicists measured the physical size of a proton, the core of a hydrogen atom, by bouncing electrons off of it or observing how electrons orbited it. And for decades, they got a very consistent number for its radius, about 0.877 femtometers. Standard physics was totally happy.
Very happy.
But then, around 2010, a team at the Paul Scherrer Institute decided to measure the proton using muons instead of electrons.
A muonic hydrogen experiment.
Right. A muon is essentially an electron's heavier cousin. It has the exact same charge, but it is 200 times more massive. Because it's so heavy, it orbits the proton much, much closer than an electron does. The researchers figured that because the muon is hugging the proton so tightly, it would give them a much more precise measurement of the proton's radius.
And the result literally broke the physics community.
Completely broke it. The muon measurement came back at roughly 0.841 femtometers, a 4% difference. Now, 4% doesn't sound like much to a layperson, but in quantum electrodynamics, a 4% discrepancy is the equivalent of a massive earthquake.
It's unfathomable.
A proton is a fundamental particle. It cannot change its physical size just because you look at it with a heavier particle. It defied all standard models.
The Standard Model had absolutely no mechanism to explain why the proton appeared to shrink. But quantum vacuum relativity solves this puzzle naturally and elegantly.
How does a buzzing square wave explain a shrinking proton?
By acknowledging the unit harmonic operator and that strict frequency cutoff we discussed, the key VSL, the framework reveals that the physics community had fundamentally conflated two entirely different physical boundaries.
Two boundaries.
Yes, the framework distinguishes between the standard electromagnetic radius, the EMR, and a newly defined boundary called the quantum vacuum equilibrium radius, or QVER.
Let me make sure I grasp this. Are you saying the electron and the muon are actually measuring two entirely different borders?
Yes, they are. Think of a proton not as a hard, solid billiard ball, but as a dense core surrounded by an energetic atmosphere. When you use a light, distant electron to measure the proton, you are measuring the outer edge of its electromagnetic influence. You are measuring the EMR.
Which gives us the larger 0.877 number.
Correct. But when you replace the electron with a heavy muon, the muon orbits so tightly, so deep inside that atmosphere, that its extreme mass deeply polarizes the quantum vacuum immediately surrounding the proton.
Oh, wow.
The muon actually penetrates past the standard electromagnetic boundary and interacts directly with the quantum vacuum equilibrium boundary, the QVER.
So the proton isn't physically changing size despite us. Our standard models just lacked the mathematical vocabulary to recognize that there were two distinct structural boundaries to measure.
Exactly. We were using two different rulers to measure two different phenomena and getting angry that the numbers didn't match. Quantum vacuum relativity provides the explicit mathematical tools, derived straight from Method 1, to calculate both the EMR and the QVER perfectly from first principles. The puzzle simply ceases to exist.
That is an incredible vindication of the theory. And the framework doesn't just solve problems at the subatomic scale. The sources show that if we scale the math all the way up to the cosmos, it tackles an even bigger crisis, the Hubble tension.
The Hubble tension is arguably the biggest crisis in cosmology today, bar none.
Let's break the tension down for the listener. The universe is expanding, and the rate at which it is expanding is called the Hubble constant. But we have a massive problem.
A huge problem.
When astronomers measure the expansion of the local universe by looking at nearby supernovae and pulsating stars called Cepheid variables, they calculate one speed. Let's call it a fast expansion rate.
Roughly 73 kilometers per second per megaparsec.
Right. But when cosmologists look at the cosmic microwave background, the faint, lingering radiation from the Big Bang, which represents the early distant universe, they calculate a significantly slower expansion rate, around 67 kilometers per second. Again, two different numbers for what is supposed to be a fundamental constant of the universe.
And just like the proton radius, standard cosmology cannot reconcile this. The error bars on both measurements have gotten so tight that we know for a fact neither team is just making a mathematical mistake.
The discrepancy is totally real.
It is real. Standard general relativity, with its smooth, unbroken vacuum, cannot explain it.
But Method 2 can.
Yes, Method 2, with its macroscopic, coarse-grained approach, provides the solution. By properly factoring in the scalar condensate and the spectral energy density of the vacuum, the framework naturally recovers the Hubble constant.
How does it do that?
It shows that the vacuum energy isn't just a static, empty void. It has a dynamic spectral density that influences expansion over vast cosmic timescales. The framework actually predicts the early universe value seamlessly from first principles.
It derives the expansion rate from the inherent structure of the vacuum itself.
Furthermore, it solves the infamous cosmological constant problem.
Oh, the 120 zeros problem.
Yes. In standard physics, when you try to calculate the energy of the vacuum, the theoretical prediction is 120 orders of magnitude larger than what we actually observe. It has been called the absolute worst prediction in the history of physics.
120 zeros of error. That's a spectacular failure.
But by utilizing the QVSL cutoff limit and the equilibrium condition of Method 2, quantum vacuum relativity derives dark energy directly from the vacuum's spectral properties.
So dark energy isn't just a placeholder anymore.
Exactly. Dark energy is no longer this mysterious, unknown outward push invented just to make the math work. It is revealed to be the inherent cumulative pressure of the quantum vacuum itself, bounded tightly by the QVSL. The math aligns perfectly with observational data.
I just want to pause and note the sheer, staggering scale of what we're discussing here. Think about the flexibility of this mathematical framework.
It's unparalleled.
This single set of equations uses scaling techniques to calculate the exact, minute boundaries of subatomic particles, solving the proton radius puzzle, and then turns around, uses the exact same foundational logic, scales up, and calculates the expansion rate of the entire universe. The sources even mention using the Milky Way galaxy as a galactic reference particle.
A GRP, yes. Treating an entire galaxy as a single particle within the macroscopic framework to model cosmic expansion. It successfully links the infinitesimally small to the unfathomably large, resolving anomalies at both extremes, without breaking a single established law of classical physics in the middle.
Okay, we are coming to the end of our deep dive into the source material today, and I really want to summarize this incredible journey for the listener.
It's been quite the ride.
We started with a shattered picture of reality. On one side, the chaotic, boiling, jumpy quantum vacuum where virtual particles pop in and out of existence. On the other side, the smooth, elegant, clear gelatin of general relativity where planets glide in continuous curves. And for a century, bringing them together caused the math to explode into infinities.
Until we found the bridge, the unit harmonic operator, theta of t.
We saw how if you use the method 1 zoom lens and push all the way into the Planck scale, that bridge looks like a jagged, rapidly oscillating square wave, built exclusively out of odd harmonics, jittering with the constant birth and death of matter and antimatter, bounded only by the universe's ultimate speed limit for vibration, the QVSL.
The pixelated foundation of reality.
But we also saw how, if you step back and use method 2, that exact same math undergoes beautiful spatial averaging. Because the universe is fundamentally lazy and seeks the lowest energy state, it generates a scalar condensate.
The antique glass.
Right, the antique glass. The law of large numbers takes over, the trillions of rapid jitters cancel each other out, and at our human scale, that chaotic square wave averages out to a perfect, smooth, constant one.
The jagged pixels disappear into the average, and the flawlessly smooth photograph of our continuous reality emerges. The effective metric operates exactly like standard general relativity.
It is a profound unification. But before we sign off, there is one final, genuinely mind-bending implication buried in these sources that we really have to share. A provocative thought for you, the listener, to take with you today.
Yes, because quantum vacuum relativity explicitly proves that the fundamental nature of the space-time vacuum is discrete and harmonic at the microscopic level. It predicts something astonishing about the nature of gravity itself.
What does it predict?
The math inevitably leads to the prediction of a discrete structure of gravitational acceleration quanta.
Let me put that into perspective for you. From the moment you were born, you have experienced gravity as a smooth, continuous, unbroken pull. It's the invisible fluid force hurling you in your chair right now. You feel it as a steady, reliable pressure. But if this framework is right, at the absolute smallest microscopic scales, gravity doesn't flow.
It stutters.
It stutters. It operates in tiny, discrete clicks, or quanta. The pull of gravity is not a smooth ramp. It is a staircase with impossibly tiny, rigid steps. Now, obviously, we do not currently possess scientific instruments sensitive enough to measure a gravitational stutter at the incredibly tiny Planck scale.
Not yet. But because the framework provides specific mathematical values for these quanta, it is a clear, definitive, falsifiable target waiting for future experimental technology.
Like a massive interferometer.
If they build an interferometer or a gravitational wave detector sensitive enough, they will literally be able to feel the universe clicking.
It is a total paradigm shift in how we understand our physical reality.
It forces us to reevaluate every single physical interaction.
It really does. So I will leave you with this final thought. Later today, when you are walking to your car, if you fumble and drop your keys, I want you to watch them fall to the pavement. And as you watch them, ask yourself, did those keys fall in a perfectly smooth, continuous, unbroken line? Or did they just take trillions upon trillions of tiny, discrete, jagged quantum steps to hit the ground? Thanks for joining us on this deep dive into the source material. Keep questioning the fabric of reality.